Okay, so we start from where we left off in the previous video. We will now prove this proposition. In this proposition, we are given a graph G that has at least one edge, and for that graph, we have to find a subgraph H whose minimum degree is strictly greater than its average degree, and average means this average epsilon, and that is greater than or equal to the average degree of G. So we will construct the graph subgraph H in this way. We construct a sequence whose first term G naught is defined to be equal to G, then we have G1, G2, etc. of induced subgraphs of G as follows. If there is a vertex Vi in Gi such that the degree of the vertex is less than or equal to, is it less than or equal to or greater than or equal to? Since we want this, okay, so less than or equal to the degree of, sorry, it's not degree, average degree of Gi, then we define Gi plus 1, the next graph in the sequence, to be the graph obtained from Gi by removing the vertex Vi, and along with that, of course, all the edges incident on that vertex. Okay, now if we do this, what happens to the average degree of Gi plus 1? Let's see. Note that by definition the average degree is equal to the number of edges of Gi plus 1 divided by its number of vertices. Now, since we have removed Vi, so that means from the number of edges in Gi, we have to subtract the degree of Vi, because all the edges incident on Vi have been removed. So that many edges, how many edges are incident on Vi? By definition, that is the degree of Vi. So that has to be subtracted from the total number of edges in the original graph Gi. And we are having one vertex less, so number of vertices in Gi minus 1. Now we apply this inequality here. So this is less than or equal to this, So this thing will be greater than or equal to this minus epsilon of gi divided by minus 1. Minus, now we can apply the definition of average degree here. Now if we simplify the expression, we ultimately get the number of edges can be taken common out, minus 1 after doing taking LCM and doing all those things, divided by gi. So these two factors, they cancel out and we are left with number of edges in gi divided by the number of vertices in gi, which is nothing but the average degree of gi. So we have got the inequality that the average degree, in fact let's just write it. gi plus 1 is greater than or equal to the average degree of gi. Now where will this sequence, the way we are constructing this sequence, where will it end? If there is no vertex vi in gi such that the degree of vi is less than or equal to the average degree of gi, then we stop and let H be the graph gi. Now note that we are in a finite graph. The original graph G is finite. So in the very first step, you would be looking for a vertex V in G naught, which by definition is G, whose degree is less than or equal to the average degree of G. If you cannot find any such vertex, then in this sequence there will be only one graph, and that is G itself. Otherwise you will find a vertex and you will remove that vertex, and once you remove the vertex, the average degree of the new graph will be greater than or equal to the average degree of the previous graph. Okay, so then in the new graph you will start finding again another such vertex. But the thing is that since we are in a finite graph, at one point we will run out of vertices whose degrees are less than or equal to the average degree of that graph where we are finding that vertex. The thing is that this will happen because we are in a finite graph. So since we are eventually bound to actually run out of all vertices if we keep on removing things, so clearly we will also run out of vertices satisfying these inequalities, and that is the point where we stop and call that final graph H. Finiteness of the original graph makes sure that this process will stop after a finite number of steps. In other words, this sequence of graphs is finite. So in fact, let's just write that since G is a finite graph, the sequence is finite, and so in any case H exists. That is, in any case the process by which we are forming these graphs, induced subgraphs, the process must stop at some stage and we will in fact have H. Now we have epsilon of H greater than or equal to epsilon of G. Why? Because we have just now shown that the operation of removing a vertex does not decrease the average degree. It either keeps the average degree same of the resulting graph, same as the previous one, or it increases the average degree. That is this thing. And since we are going on removing more and more vertices, so these inequalities will come together and they will tell us that the final graph in our sequence has average degree greater than or equal to the average degree of the previous graph, which itself is greater than or equal to the average degree of its previous graph. So like that we will eventually reach G, and that's why we have this inequality. We can write the reason here like this, because Gi plus 1 is greater than or equal to epsilon Gi. For what type of I, that is understood. Okay. Now what else can we say about this graph? Note that we have in fact got one of the inequalities, namely this second one. Now what? Since we have obtained H by ultimately removing vertices from the original graph in steps, of course, but we have removed a number of vertices from the original graph, or we may not have removed in that case where the original graph itself qualifies to be H. But in any case, since in general we are removing vertices, so it may happen, because we don't know yet, no? That H ultimately has nothing in it, that all the vertices get removed. Will that happen? That in fact will never happen, and we have to argue why. Note that since epsilon of k1 is the graph having only a single vertex and no edge. Since it has no edge, let's just write the formula for this average degree. This will explain why the average degree for this one is 0. There is no edge, so that is 0, and there is only one vertex, so this is equal to 0, and this is strictly less than epsilon of g. Why? Because it's given in the hypothesis, it's given that G is a graph having at least one edge. So if we write the corresponding formula for epsilon of G, we would be dividing the number of edges in G divided by the number of vertices in G. So in the numerator, we will have a positive integer. We won't have 0. So that's why this ratio is strictly greater than 0, and this is less than or equal to epsilon of h. H is non-trivial. Okay, H is non-trivial. That means H itself must have some edge. Although we are going on removing vertices from G to ultimately form H, correspondingly edges are also getting removed, namely those edges that are incident on the vertex that is being removed. But ultimately in H, we will have edges because this ratio has to be greater than 0. So in the numerator, we have the number of edges that has to be positive, and that's why the graph itself must have something in it, some vertex, because without any vertex there won't be any edge. In particular, H is non-empty. H is not the empty graph. Further, since there is no vertex V in H such that degree of V is less than or equal to the average degree of H, because that's why we stopped the process at H, right? If we found a vertex that satisfied this inequality, we would have removed it from H and then the process would have continued. So that has not happened, and that's why we have H, we have stopped the process at H. So there is no vertex that satisfies this, which means that for all the vertices, their degrees are strictly greater than this epsilon of H. In particular, the smallest degree of G, the smallest degree of H also then has to be strictly greater than epsilon of H. We have, in fact, let's just write a little more. Degree of V strictly greater than epsilon of H for all V belonging to the vertex set of H. That is the smallest degree of h, which also is ultimately the degree of some vertex, strictly greater than the average degree of h. So this is the first inequality that we wanted. So this completes the proof, and it also completes this section. We are now going to have a look at the next section. Paths and cycles. Special types of graphs, paths and cycles, they are called, and they will help us study the structure of a graph in detail. These graphs called paths and cycles are by definition very simple, but nevertheless they are of great use. A path is a non-empty graph whose vertex set is V, H set is E, where the vertex set has some vertices. Non-empty, that means the vertex set has to be a non-empty set. It has some k plus 1 vertices, and the edge set looks like this. These are the edges, x0, x1, x1, x2, like that it will go. Xk minus 1, xk, where the xi are all distinct. So we can, although you can see what a path will look like, but still we can draw a figure like this. So let me put one more. So the graph looks like this, and the graph itself says why it's called a path, because it looks like a path. And again I am saying that of course you can draw this in any manner you want. It need not, the points need not be on a straight line. Okay, you can draw them in whatever way you want, and also the edges you can draw in whatever way you want. They need not be straight line segments. So that's a path, and the vertices x0 and xk are called its ends. Called the ends of P. whereas the vertices that lie between x0 and xk are called the inner vertices of P. Quite natural names. Okay, from the names we can clearly see and remember what they are. The number of edges of a path is called its length. A path or since isomorphic graphs are not considered to be anything different, we can write the path. The path of length k is denoted by pk, p superfix k, where k can be any non-negative integer. Note that according to the definition of a path, the set V needs to be non-empty. That is the only restriction on V. V can have exactly one point also, in which case the path just looks like this, a single vertex. That is also one extreme case, but by definition that is a path whose length is 0 because there is no edge. If you have a path like this, then it's a path of length 1, there is only one edge. This is a path of length 2, this is a path of length 3, and so on. So the path of length k is denoted by pk. Note that k is allowed to be 0, and in this case we have P0, which is nothing but K1, the complete graph on one vertex. We often refer to a path by its vertices or by the natural sequence of its vertices. Writing say p equal to x naught, x1, etc. up to xk, and calling p a path from x naught to xk. So this is a new notation. If we see anything like this, where this x naught, x1 up to xk, these are distinct vertices, then that means it's this path. Okay, so the natural sequence in which the vertices are appearing in the path, that is used, and we understand that these are the vertices, and adjacent vertices adjacent in this list or in this product looking thing. X naught is adjacent to x1 because it comes just beside x1. They are adjacent in the graph, that is, there is an edge between them. Like that, x1 and x2 are adjacent here, so x1, x2 is an edge in the path. So this is the notation. So we also call this a path from x0 to xk, or a path between x0 and xk. These terminologies are quite natural because it's like a path between two places, or a path from this place to another place. Natural sequence, there is something else to say about this. More specifically, one of the two natural sequences. That is, when we write the vertex set of a path, its vertices come in some sequence, but of course the path itself determines two natural sequences, one which starts from x0 and ends at xk, and the other which starts from xk and ends at x0. So we have to choose one of them, stick with it, and then we can use this. So that means instead of writing like this, we can start with xk also and end with x0. That's what this is saying. One of the two natural sequences, x0, x1 up to xk, and x0. These two things denote the same path. And one more thing is this: still it helps to first choose the sequence that we want to use in writing a path, because once we do that, then we can say that, say, the path has a first vertex which satisfies some other property. We can use such things. It becomes very natural when we speak of things like, for example, you have a path where all the vertices except, all the inner vertices have degree 2, but you may have a vertex that is adjacent to say something else. So you can say that in this path let 2 be the smallest positive integer for which x2 is having degree at least 3. You can also say it because in writing this path, we must have followed this sequence, writing the path like this. Then you can also express that statement like this. Let x2 be the first vertex having degree, first inner vertex having degree at least 3. So then such things can be said. So that's what the author is writing. Still, it helps to fix one of these orderings. Of the vertex set of P notationally. We may then speak of things like the first vertex of P with a certain property etc. Okay, so let us now draw a graph and see one path in that graph. One is given. We can in fact draw any graph, but let's just draw the one that is given in the text. With quite a few vertices. Oh, there is that one also. Okay, so this is a graph. Let me make the vertices more prominent. So where there are 1, 2, 3, 4, 5, 6, 7, 8 vertices, and you can see the edges. In this you can see that somewhat the bolder edges, okay, they are forming this path. Between this vertex and this vertex, the path goes like this. Okay, so we can consider a path which is a part of a graph. So the original graph is G, and this is the path. In a graph G. Oh, and in fact this is not just any path, this is a path of length 1, 2, 3, 4, 5, 6. So P equal to P6 in a graph G. Now there are some quite natural notations that one can use while writing subpaths of a path, which are subgraphs of a path and which themselves are paths. So, and the notations are like this: for integers I and j satisfying these inequalities, we write by pxi, we mean the subpath of this path starting from x0 and ending at xk, from x0 to xk, the subpath of that path which starts at x0 and ends at xi. Okay, that is the path joining x0 and xi. Like that, by xip we will mean the path between xi and xk, that is the part of the graph that lies on this side of xi. That's what we mean by pxi, and by this we mean the part of the path that lies on the right side of xi, I mean at least in this order. So these notations mean this thing, and xi p xj, of course now you can almost guess what this is. It's going to be the path, part of the path joining xi and xj, and by p naught we mean the part of the path obtained by removing the ends from the original path, keeping only the inner vertices. Then Okay, let's go consistently. Pxi 0, it joins x naught and xi minus 1. xi0p, it joins xi plus 1 and xk. That is, when you see a superfix 0 superscript, or in fact we cannot say superscript because it's being written on top of the, just above the symbol. So when you see that, that point should not be, that vertex should not be considered. Everything else that comes after it, they are considered. So that means here the things are starting not from xi but from xi plus 1. Like that, here the things are not ending at xi but they end at xi minus 1. And then just like that, xi0 pxj 0 is the path joining xi plus 1 and xj minus 1. We write these things for the appropriate subpaths of P. Yes. We use similar intuitive notation for concatenation of paths. For example, if you take the union of a number of paths, which ultimately again becomes a path, then that can be, it can be written notationally more simply like this. If the union say px xqy and yr, looking at these notations you now know what px is. Px is a path that starts somewhere, ends at x. xqy is a path that starts at x and ends at y, and yr is a path that starts at y and ends somewhere. Okay, so this is concatenation of paths. This union of three paths is a path then we denote it by this symbol px q y r. So x and y show the points where the paths are joined to each other. For example, we can draw this graph. I am drawing the exact things as given in the text because you should not be deprived of those things, no, because the author may have something special in mind when he chose these particular graphs, which may not have been expressed explicitly in the text, but if you look at the figure, you may find something else than what is being said here. So for that reason, we are not arbitrarily drawing our own graphs, but rather sticking to whatever Diestel has provided. There is this triangle also, and again these things can also be drawn without using ruler, but it looks good with ruler. So say you have here, this vertex is x, this is y, and this is suppose z. So one path you have is this, between x and y, and the other path, this one, is between y and z. So these two paths can be concatenated to form a single path. And if this path is this P between x and y, and this path between y and z is suppose Q, then the total path obtained by combining these two paths will be denoted like this: xp y q z. Okay, then there are some more notations and terminology. Given sets of A and B of vertices, A, B of vertices, we call a path P equal to x0, x1 to xk, and AB path if the path ends at A and it starts at A and ends at B, at some vertex of B, and does not interfere anywhere else in A and B. Specifically, we say this if the only vertex common between P and A is x0 and the vertex common between P and B is xk. We then say that the path is an AB path. For example, if say in this graph itself, if you say take A. Let's just for the time being, for our convenience, let's label the other vertices also 4, 5, 6, and say A is equal to 1x3 and B is equal to 3, 6. Okay, instead of taking 3, 6, you can take y4. Okay, y4, 5. Then this P, this thing, this path of length 2, this P is an AB path. Why? Because the only vertex common to A and P is X, where the path is starting, and the only common vertex to the path P and B is Y, where the path is ending. So if this is our A, 1x3, and this is our B, then you can see that, okay, so this is A and this is B. Keep in mind that A and B are not graphs. A and B are sets of vertices, but of course on the graph they can be identified like this. Then the path is an AB path. Okay, it starts from A and it ends in B somewhere. As before, we write AB path instead of AB path. That is, if one of the sets is a singleton set, then we don't write the single element within curly brackets. So we simplify the notation further, etc. Two or more paths are said to be independent we say if that two or more paths are independent if none of them contains an inner vertex of the other. In this example, paths P and Q are independent. Path P is this and Q is this. There is only one inner vertex in P, which is 2. The vertices X and Y are its ends. And Q has two inner vertices, 4 and 5. Ends can be common, but inner vertices are not common. So here P and Q are independent. Of course, it may happen that the ends also may not be common. For example, if you consider P and say you consider the path 3, 6, Z, then here no vertex is common. They are also independent. But n vertices can be common, still we call them independent. Two AB paths are independent if and only if their common vertices are exactly A and B. Are there only common vertices. For example, if you take in place of A, you see AB paths means this A is a single vertex, this B is also a single vertex. That means in this case AB path, both the sets are singleton sets. So if A is this vertex X and Z is say this vertex, B is this vertex Z, then there are two AB paths here. Actually there are many AB paths, but let's consider two of them. One of them is this X136Z. The other of course is this X2Y45Z. These two are independent because the only common vertices to them are their n vertices. The inner vertices of the upper one are 1, 3 and 6, and for the lower one they are 2, y, 4 and 5, and these two there is no vertex common to them. So these two AB paths are independent. However, the AB path X136Z and X2Y36Z are not independent because there the inner vertices 3 and 6 are common to both the paths, so they are not independent, although they are also two XZ paths. Given a graph H, we call a path P and H path. Okay, a path is called an H path if P is non-trivial. And meets H at exactly its ends. So, okay, let's just wrap this up. Let's take some other example. Say we have a graph like this. And say this is H, and you consider, let's name these vertices X and Y. Now you consider the path P, which starts at X and goes like this and ends at Y. Then P meets H at exactly its ends. The inner vertices and the edges incident on them are not parts of H. Okay, they are not inside H, or they are not vertices or edges of H. If that happens, then we call this path an H path. That is, an H path starts at somewhere in H, then it goes outside H and then again comes back somewhere in H. So that is an H path. And in particular, the edge of any H path of length 1 what is being stated here? The edge of any H path of length 1 is never an edge of H. Oh, okay. In particular, edge of length 1, edge by definition, edge of H path of length 1, okay. In particular, an edge of, now the sentence is somewhat confusing. Why are they saying length 1? In particular, and okay, if I write like this, in particular an edge of any H path is, okay, H path of length greater than 1. Yes, now it is making sense. Is never an edge of H. You see, suppose we have an H path, okay, whose length is greater than 1. Note one thing, that if for a moment, if we forget about this path P, forget about these vertices, then we have H. In H we also have this H path XY of length 1. This path only has ends, it has no inner vertex. So by definition, this edge XY along with of course the vertices, this is also an H path because it meets H at its ends only. Since there is no inner vertex, no question of meeting H at the inner vertices. But this edge is a part of H. However, if the length of the H path is greater than 1, that means there is some inner vertex. So the path has to go outside of H and then again come back. In that case, no edge of the H path. For example, for this H path P, these are the edges. This is one edge, this is another, this is another, and this is another. This one is not a part of the path. No such edge can be an edge of H itself. You can see why. because if this, for example, becomes an edge of H, then its other end should also be in H, which violates the very definition of an H path, because in an H path the inner vertices should not be vertices in H. So that's why they are saying, in particular, an edge of any H path of length greater than 1 is never an edge in H, never an edge of H. If P equal to x naught, x1, etc. to xk minus 1 is a path and k is greater than or equal to 3, then the graph obtained by joining x naught with xk plus, k minus 1, which is nothing but p plus x naught xk minus 1, is called a cycle. So a cycle is like this. A cycle is obtained by joining the ends of a path by an edge and making them adjacent in the process. So if we have a path like this, and if we join these two ends by a single edge, which of course requires us to introduce a new edge, then this is a cycle. You can understand why it's called a cycle. It cycles back to where it started. As with paths, we often denote a cycle by its cyclic sequence of vertices. By its cyclic sequences of vertices. Cyclic is written within brackets. The above cycle C okay. So a name is also given to this, and the graph C is equal to P plus this is called a cycle. The above cycle C may be written as this: x naught x1 up to xk minus 1, and then again x naught, because that is also an edge now, joining xk minus 1 and x naught. The length of a cycle is its number of edges. the length of a cycle is its number of edges, means it is defined to be its number of edges, that is understood, or the number of vertices. Note carefully that while the number of edges of a path is one less than its number of vertices, but the number of edges in a cycle becomes equal to the number of vertices in the cycle. That's why we are saying or the number of vertices. Did I miss anything? Oh, this k greater than or equal to 3. You see, when k is 3, then what do we get? x0, x1 and x2. So that means we will have the situation like this: x0, x1, x2, and then you join x2 and x0. So you get a triangle. However, if you just simply have, say, x0 and x1, then that will not give you a cycle, because you cannot join an edge. That will give you two different edges between x0 and x1. This is not allowed in the type of graphs we are considering. In our definition of a graph, multiple edges are not allowed. We will see those things. They are called multi-graphs later on in the book. So that's why the minimum possible value of k here is 3. Okay, now the cycle of length k is naturally just like pk, it's denoted by ck, c superscript k. The minimum length of a cycle contained in a graph G is called the girth of G. And is denoted by G of G, I think. Yes, small g of G. And the maximum length is called the circumference is called the circumference of G. Oh no, notation has been given for the circumference. Maybe there is a notation, I may have missed it. We will see later. If G does not contain a cycle, yes, what happens then? its girth is defined to be infinity. And its circumference is defined to be zero. It may look strange somewhat, but the situation is like that supremum and infimum of the empty set considered as a subset of the set of real numbers. If you go to that definition of supremum and infimum of a subset of the real numbers, then there you will see that excuse me, when the set is empty, then such a similar situation occurs. From there, I would suggest that you try to draw an analogy between that and this situation, because in this situation, although the graph is there but it does not have a cycle, then what can you possibly define the girth and circumference to be? I say it looks strange because according to the ordinary definition of the notions of girth and circumference, girth is the minimum possible length and circumference is the maximum possible length. So if there are cycles in a graph, then the girth of the graph will always be less than or equal to its circumference. However, in this case, the exact opposite thing is happening. So you can draw the analogy and you can try to understand why this type of why we have defined girth and circumference in this extreme case to be having the opposite order. An edge of a graph that joins two vertices of a cycle. In fact, an edge of a graph, we can simply also say an edge, but ultimately it's in a graph. So an edge of a graph that joins two vertices of a cycle but is itself not an edge of the cycle is called a chord of the cycle. So let's draw the example that is given here. Okay, so this is the graph in which you can see that the somewhat more pronounced edges, namely this one, 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 and this one. So they form a cycle along with, of course, the vertices that come in between, and these are, say, two vertices. So they are also adjacent, they are joined by an edge. However, this edge, although it's joining two vertices of this cycle, is itself not an edge in the cycle. So this is a chord of the cycle. And in fact, we can write a cycle C8 2, 3, 4. So there are 6 vertices, 7, 8. A cycle C8 with chord XY and induced cycles C6 and C4. The graph also has two induced cycles, that is induced subgraphs which are themselves cycles. This is C6 and this is C4. Okay, so we can continue writing here. Thus, an induced cycle that is a cycle that is an induced subgraph of G has no chord. It cannot have a chord. For example, these induced cycles in the graph G, they don't have chords. Why? Because if there is a chord, then since it has to be an induced subgraph, that chord should also be a part of the subgraph. When we consider an induced subgraph, then from the graph we not only take all the vertices that we need, but we also take all the edges that can possibly come with those vertices. In particular, if in the original graph there are two adjacent vertices, then in the induced subgraph, if they are still vertices, there also they need to be adjacent. So in this particular graph, the cycle that we have considered, this C8, it's not an induced cycle, because otherwise XY would have come, and in that case it will not be a cycle at all. So that means if we have an induced subgraph which itself is a cycle, then it cannot have a chord. Okay, now we come to a proposition. The first result of this section, with this we will end this video. We will state and prove it. A very interesting one. Every graph G contains a path of length delta G and a cycle of length at least delta g plus 1, where delta g is the minimum degree of the graph. So whatever the graph may be, there will always be a path of that length and a cycle whose length is at least this. So we will start by considering a path of maximum length in the graph. Such a path will always exist because our graph is a finite graph. So a graph with maximum possible length, a path with maximum possible length will always exist. There may be multiple such paths, we are choosing one of them. So we start the proof like this. Let x0, x1, etc. to xk be a longest path in the graph. A longest path we are saying because there may be multiple longest paths, multiple paths of maximum possible length. Okay, let us now draw it. We are actually drawing only a few vertices, but you have to understand that there are others in between. There are not in particular only 6 vertices, there are others in between. Okay, so this is x0, this is say xi, this is xk. So xi is somewhere in between, but xi is a special type of vertex. Now okay, fine, so this is a path of longest possible length in the graph G. Now that we are now going to make a claim, namely that note that the neighbors of xk all lie on this path. Why? We are claiming that whatever neighbors xk has, for example, this itself is a neighbor of xk, this vertex lies on the path. We are claiming that the other neighbors of xk also lie on the path. The reason is that if say you have a neighbor of xk that is not lying on the path, then you get a longer path. But according to the way we have chosen this path, it's a path of longest possible length in the graph. So that will be violated, maximality of the length of this path. So that's why xk cannot be adjacent to any vertex that is not lying on the path. It must be adjacent to only vertices lying on the path. So that's why we are saying note that the neighbors of xk all lie on this path. In fact, we can write a little more. Otherwise, we shall have a longer path in the graph than the chosen one. Okay, so say this is one neighbor, just simply saying, and say this is also one neighbor. Keep in mind that these two vertices are not adjacent. Xi is just some vertex in between. Okay. Now, what conclusion can we draw from this situation? Then, K is greater than or equal to, what was it? K is greater than or equal to degree of xk, which of course itself is greater than or equal to the minimum possible degree of g. Where are we getting the first inequality from? You see, we are saying that the neighbors of xk are all lying here. Now, how many points do we have available to us, starting from x0 and ending at xk minus 1? They are available for us to be neighbors of xk. May not be all of them, but whatever neighbors xk has, they are from that list, from among these vertices. Okay, so the total number of vertices here is k. Among them, some are neighbor, so they contribute to the neighbors of xk contribute to the degree of xk. So the degree of xk can be at most k, or it is smaller than k. So that's why k is greater than or equal to degree of xk, and degree of xk is some degree, and this is the minimum possible degree of the graph. So this inequality is natural. It comes from the definition of small delta g. Okay, now what are we getting? You see, what is the length of this path? The length of this path is the number of vertices minus 1, because the length of a path or the number of edges of a path is 1 less than the number of vertices. Note that the length of this path is k. Total number of vertices is k plus 1 minus 1. So this is k. I think the of length, I think here it should be at least or if you want, I am not sure whether I have taken this down correctly. If there is at least is not there, then fine, we have got a path of length k which is greater than or equal to delta g. So there you can find a subpath of length exactly equal to delta g. So things are fine. But now we have to argue that there is a cycle whose length is at least delta g plus 1. So for that, let xi be the first vertex there is a cycle of length. Are we missing something? Yes, there is a cycle of length at least delta g plus 1. After writing that, in brackets you write provided delta g is greater than or equal to 2, because otherwise that part of the second part of the statement does not make sense. That is, after stating the theorem the way we have stated, you write this additional thing, provided delta g is greater than or equal to 2. Okay, now since delta g is greater than or equal to 2, so that means there is no vertex of degree 1 or 0. In particular, xk itself cannot be a vertex of degree 1. Already it is adjacent to its neighbor in the path, but besides that it should also be adjacent to something else, because otherwise its degree will be equal to 1, and that something else, as we have seen here, due to the longest nature of the path, that something else must be from here, from these vertices. Let xi be the first such something else. Okay, that is, I is the smallest non-negative integer such that xi is adjacent to xk. The other vertices that come before xi in this list, they are not adjacent to xk, and we know that one such I exists because one such I is k minus 1 itself, but I is the smallest such I. So that's why we have written let xi be the first vertex adjacent to xk. Note that we can say first vertex because we have chosen an order of the vertices in which they appear in the path. So naturally we are starting things from here and going towards the right hand side. So in that scheme of things, xi is the first, means from this side it's the first, not from that side. Be adjacent to xk. Then we claim that the length of the cycle, then the cycle obtained from this path and the edge xi xk, we are talking about that cycle. Length of the cycle xi plus 1 xk xi is okay. So what will the length of the cycle be? The number of vertices this path has. Now, I mean this cycle has. How many vertices are there between xi and xk? Excluding xi, the number of vertices is k minus I. So including xi, it will be k minus I plus 1. Then we claim means it can be seen. Then the length of the cycle is k minus I plus 1. Our claim is that this k minus I plus 1 is actually greater than or equal to delta g plus 1. Suppose contrary to that, suppose k minus I plus 1 is strictly less than delta g plus 1. Okay, then if that is the case, then k minus I is strictly less than delta g, and so degree of xk, which is less than or equal to k minus I, will be strictly less than delta g, a contradiction. Okay, so our supposition of course directly implies this. You can cancel 1 from both sides, but now look at this. You see, because of the nature of things, the neighbors of xk are confined in this part only, between xi and xk minus 1. Okay, now if k minus I becomes less than delta g, then okay, how many vertices are there between xi and xk excluding xk? K minus I. From among them we have the neighbors of xk, that means degree of xk will be less than or equal to k minus I. Now if k minus I is strictly less than delta g, then this degree becomes strictly less than delta g, but that contradicts the very definition of delta g as the minimum possible degree of any vertex in the graph. So this contradiction shows that our supposition is wrong. That is, k minus I plus 1 should be greater than or equal to delta g plus 1. So we have found a cycle of length at least delta g plus 1. Note that how this extra condition makes it necessary for us to have a cycle in the first place, because xk cannot be of degree 1, and that's why xk must have a neighbor other than xk minus 1, and that neighbor must be lying on this path. So we are bound to have a cycle. So that is also one particular consequence of this result, that we are always going to have a cycle if delta g is greater than or equal to 2. If the minimum degree is greater than 1, then we will always have a cycle. And if you just look at the statement of this proposition, it's not immediately apparent that this is the case. Every graph G contains a path of length, that is the minimum degree of the graph, and a cycle of length at least minimum degree plus 1, provided the minimum degree is greater than or equal to 2. So this completes the proof of this proposition. So in the next video, we are going to end the video here itself. In the next video we shall continue with the other things that come after this. So that will be all in graph theory for today. So this is me, Lucifer, from a mathematical room. Have a nice night.